Good morning, everybody. Hello again. Talking about sediment, a little different topic, but it integrates with hydrology so well because all the cause of sediment is the hydrology, right? So we have sediment, 2D sediment included in GSSHA. Also in the stream of GSSHA process, stream process in GSSHA too. So we'll talk about those. So there are, like we talked yesterday about physics-based and empirical, all these things. There are several equations of sediment transport. Among those, some are like for longer period of time, right? And it gives the rate, average rate in annual basis or something like that. And these are something like USLE, best equation, which is an empirical relationship of sediment rate calculation. And it usually defines, and it does have that parameter like we talked yesterday, which is empirical based. But again, it relates to some of the physics of the watershed, like land use, crop type, soil type, the agriculture, management, all those things defines that soil erodibility factor. So if it is kind of sand, those kind of soils, the erosion is more likely to happen because of the energy that comes through, like velocity of water, right? So the erodibility of the sediment in the equation in that case varies from 0 to 1. So for those kind of soils that's easily erodible, the coefficient that the parameter of K, the erodibility is higher. But in GSSHA, it deals with events-based simulations. So it has the functionality to calculate the erosion in a small time step, like the time step we provide for GSSHA overall model, right? So it gives the erosion and deposition, which is all distributed in nature. And also, there are a whole lot of equations or options in GSSHA. Some are empirical, some are completely physics-based, and some are those equations that really doesn't need any input of parameter, which are all already default in the GSSHA. Oh, okay. This is a general highlight of overall picture how the sediment functions in GSSHA. There is sediment overland erosion. The overland erosion basically happens by, we call it source of sediment, happens by two main, what triggers that sediment in overland? The source is, one is rainfall impact, and the next is the velocity, all that energy of the hydrology itself, and that is the series stress, right? So if the series stress is higher than critical series stress, then there is erosion or trigger that the particle which is attached that gets detached from the original mass and then is a source of sediment at that point. And then in GSSHA we have the deposition. There are trap efficiencies that we utilize. GSSHA all coding and how we implement the process, it goes, there's a long history. Some of the equations really developed, so-called trap efficiency. We applied that for deposition of the suspended sediment in the volume or control volume in that particular cell. But there is also functionality that the deposited sediment at times, again, it goes back to the flowing water, so-called re-entrainment, right? And there is another function, so-called transport capacity. So if you have the mass of sediment as certain grid cell, we have the calculation of transport capacity. And for this transport capacity, basically USLE, all those equations are empirical, and along with so many equations that we use in GSHA and we tested in GSHA are for the transport capacity. So we'll come to those transport capacity equations as we go along this slide. And there is, after the overland mass of sediment is transported with some routing equation, and then it goes to the stream. And in this stream, like the hydrology portion is 1D, there is a process that transports the sediment from one link to another and towards the outlet. But if there is reservoir in between, then it has the mechanism how to deal the sediment in reservoir as well. And if you look like, if you have the long-term simulation, for example, 10 years, you did whole simulation for 10 years, and it makes sense. There is a landscape evolution after a long time, showing that where the topography has degraded or where topography has, the elevation has enhanced. Those kind of functionality is there with time. But even in certain event-based, when there is big disaster or something like flood flow or something like that, it can change the topography. Dramatically, those kind of effects we can see in the output. So in GSHA, sediment doesn't have to be a lump kind of like all just like sediment, but we can distinguish the sediment in terms of particle size. So it can be any number of particles, right? For example, silt are very fine, sand are coarser, but there could be gravels, all those things. And you can also define the physical properties in terms of the particle size, like specific gravity. It changes from one particle to another. So that can be defined in the input. And it takes account in the process of erosion in GSHA. Like I said earlier, sediment detachment happens by rainfall impact and overland flow limits. The overland flow limit is if the shear stress is bigger than the critical shear stress, then the sediment happens to, trigger from that point. And transport capacity is nothing but to see if the amount of sediment load at particular grid cell is the overall energy is able to transport that or not. Even the source is available, if the transport capacity or energy isn't there to transport that from one grid cell to another, then it doesn't take all with the flux. It leaves what it can. It takes away what has the capacity. So that's called transport capacity. Basically, the transport capacity is Richardson equation, England-Hansen equation, and there are multiple series stress formulas. Basically, these series stress formulas, why they are called series stress formulas is because of it's directly related to energy. And actually, these are kind of empirical relationships that's derived in laboratory. So having said laboratory, the scale has definitely some effect on when we go to the catchment size. So we did a lot of testing whether these laboratory-based transport equations apply in bigger scale. And we found that certain scaling factor has to be utilized for each transport equations, which is what we published around several years ago. There's a big flux coming there. But the sediment is well protected. See the terrace, so it doesn't flow away. So that takes account of these, the erodibility factor, the terrace kind of farming. It helps like preserve the sediment, so the coefficient is lower for that. Those kind of things. It's very practical, cause and effect relationships. Like I said earlier, like cover conditions plays a role in erodibility factor, right? And soil particle, like sand particles, are more erodible than cohesive other types of sediment like clay, probably. And management, how you manage the land. For example, different type of plowing and all those things. Also, how you develop man-made kind of structures, concrete and all those things plays a role, how much sediment ultimately goes downstream. Erosion forces, these are again back to rainfall intensity, discharge, shear stress. So for the rainfall impact, it actually depends upon the rainfall drop size. So basically, it's kind of empirical relationship. So if the drop size is bigger than what is ponded on the ground, then the sediment starts to trigger from that location. But on the other part, whole K, C, C defined there, these are again the coefficients or empirical, parametric values. So sometimes we can all compact all these KCCs, all those things into one, and again apply that. But how it applies is there more, canopy or not? So more canopy resists the sediment to trigger from a location. And it depends upon crop types. If it is like seasonal crops, that has more sediment, detachment possibility. But if it is like evergreen grass, that has more sediment capacity to hold the sediment back. So all these factors are empirically derived, but is well used in several equations or well-known modeling platforms like WAVE and GSHA and all those models.
Yeah, and from experience, it is sensitive to that K1.
Yeah.
It's one of the parameters.
That's
in that last slide. The catchment by rain soil erodibility is one of the parameters that is sensitive. Take a look at.
Yeah. But what is done in GSHA is that the detachment by rainfall, all these parameters are default in the code. And there is a reason how we default the values. We take all these parametric values from another well-used numerical model like WIP, and we thought we make it default that way. So the users doesn't have to worry that part, the impact due to rainfall. On the other hand, this part, the detachment by shear stress is important. And in this case, the user has to define some parametric values like A and B defined in this equation, which is A is a coefficient, B is a exponent to the difference of actual shear stress and critical shear stress. But all the time I'm talking about the shear stress. Now here, when the detachment happens is when shear stress calculated is bigger than critical shear stress. Now, critical shear stress is a value that user have to define, but it has specific values well defined for each soil type. And TC is the transport capacity in this equation. So the transport capacity, this equation T here, is defined, like I said before, by several equations. One is Richardson equation, defined here. Actually, the key parameter, again, is the erodibility factor, which Steve says is very important. Actually, it's just like every process has a dominating parameter, right? For infiltration, it's always the most dominant parameter is the hydraulic conductivity. And we define it as a coefficient, as a calibration parameter, always. And in surface runoff, in the transport equation, the Manning's roughness is the dominating parameter. Likewise, in sediment erosion process, the most dominant parameter is the scale. If you are using the transport capacity defined by.
So when we calibrated to this K here and this, and then also that detachment K. Those are two numbers we sort of calibrated and that's and adjust and try to get right.
Yeah.
It's the most sensitive of those two.
But the degree of freedom is applied to K because K is more like empirical and it's a parameter. But certain things, sometimes we define it like parameter. For example, initial soil state, right? Initial condition. Many times we see, even in literature, it's a parameter. Actually, it's not. It's a state variable. That's the initial state variable. Just like critical shear stress. It's not a parameter. It's a value for particular soil type. So, having said that, we can tweak around in the modeling to get the right answer, tweaking those state variables and actual values that is more physics based and rather not the parameters, but we do sometimes figure it, like play around with that as a parameter. But K is an absolute defined parameter, so we can use that in calibration very well. Like I said earlier, this is a complete physics-based equation, the England-Hansen, and it is all depend upon all the flow characteristics and the flow properties. And actually, you don't have to input anything in this equation. Although, because of our experience, we provide there as coefficient, calibration coefficient, which is in initial original state, probably there isn't that coefficient. Sometimes in some erosion process, we saw that if we put some calibration parameter, it gives better answer. Because there is nothing else to tweak around in this equation. You see here, B is already defined, is the width of the flow, top width of the flow. V is the velocity, H is the depth of the flow, S is slope, right? And small s is specific gravity, like we talked about. It can be defined by the user. And D is mean size diameter. So the fraction is in overall the sediment. There would be like 3 sediment types. Let's say one is clay based, another is sand based, another is silt based. So how much portion of sand, silt, clay is there as a fraction? So total number of fractions, when we add all together, it's 1. So a whole lot of other transport capacity formulation are based on laboratory derived equation, which is what we use is the stream power equations derived by Everett 1991. And we tested, that was derived in laboratory scale, like in fluid. And we tested in hydrology scale. And we saw some good result when we can directly apply that equation or not. And we also adjusted those equations in terms of situation, how we validated in our simulated results. So I think there are 4 or 5 those kind of equations that are derived as a transport capacity, and these are as follows, which is explicitly defined here. And actually, no parametric value has to be provided by the user. That's the good part of these equations, you know. And because of that, we are trying to see, just we talked like yesterday, which would be more applicable in on-gauge basis, because a whole lot of areas we even don't have what is the measurement of the stream flux, right? But coming to what is the amount of sediment is more complex, and there are really rare sites where those measurements are taken. So in that case, if you are projecting or defining how much sediment is flowing in somewhere unknown basin, then those equations play a great role. It doesn't need any parametric values.
See, Jason said he just lost audio there.
Hello, can you hear me?
I turn up the volume because it'll be echoing.
Can you hear me now? Hello? Hello?
Hello, I can hear you now.
That's good. Yeah, we went quite far. We didn't know, we don't knew that the voice is lost. So, do you want to repeat something in sediment? Did you hear something about sediment?
Yeah, I
At
heard
all.
some stuff about sediment. I just missed the last like minute and a half.
Okay, so you are good. Most of the thing I repeated, these are only the details portion, maybe defining the equation and things, but basic, what I talked in few slides earlier is the same thing we are going forward. So thank you. So again here, these are again defined in terms of the energy, right? The energy is the flux and the slope. But here, all the equations require the mean size diameter of the sediment particle, mean size diameter for different fractions of sediment. So, and all these equations within itself defines what is the parametric value and everything. That depends on the medium size diameter. So it's the same thing here for if the medium size diameter is less than this, you know, 33 micrometer, then the value is 1.4.
Right.
And the user again don't have to calculate outside the modeling platform as an input to define what is the mean size diameter. But internally, it's calculated. So having said that, these are all equations that doesn't require any parametric value input, but the reliability of these equations are defined from our experience, numerical model experience. We have defined those in a paper. I think that's listed at the end of the slides. And then once the sediment is there, which is in suspension mode, then how much sediment then can be trapped in that particular grid is a function of velocity, again, depth of water, right? And the fall velocity in that grid size also depends upon the grid dimension because it has the amount I think that something to do. What is the relevance of this grid size in this equation, Billy?
Say that again now.
What is the relevance of this dimension x grid size in this equation?
I think that's probably just like the lateral distance in terms of trying to figure out how much is gonna get trapped in there. So like if you have a. You what now?
Like falling over a
Yeah.
distance and
Yeah.
it's falling. Does it get trapped in the cell or does it pass out of the cell?
Right.
So, and the trap efficiency varies from 0 to 1. So you have total amount of sediment, and then that's multiplied by the efficiency. That amount just settles down in that grid cell, and look for another time step, whether that will be eroded or not. That's the source in that grid cell, but it may not be a parent material, right? The parent, so the beauty of all those sediment transport is there is a place down here, but the source of sediment could come from somewhere else. And those sources can overlap on the original material. So when it is doing all that sediment processes, it is particularly taking care of that original source and then deposited from other areas and all those things. Now, in a stream, the sediment, once it goes from overland to stream, we define in this present release version of sediment, we define sediment, the sand size sediment, the diameter sand size sediment. So particles bigger than the critical diameter that we define for sand all settles down in a stream. And in the stream, the settle down sediment, we calculate as per the transport capacity. That's Young's equation. But in, which is suspended, then we define it just like overland, but in one dimensional, it's advection equation. Which is again, the function of the depth, unit discharge, and these are the energies. The derivative of those in time and space is balanced in mass and continuity with the source of sediment and the lateral inflow in that particular place, taking account in the equation. In reservoirs, it's more simpler. In the reservoir, what happens is, now reservoir in GSSHA is not static, it's dynamic, because all is like flexing or expanding, and the contracting happens in terms of how much water comes to that country from upstream, right? So if there is long drought, the water starts shrinking, and that is defined in GSSHA. So sometimes GSSHA can eat up channels which is upstream, and sometimes when it shrinks down, again the channel reappears. When channel reappears, the sediment processes goes back to the original channel sediment process. But when it is gulped by the reservoir, then it acts through the reservoir mechanism. And in reservoir, what it does is all the bigger size sediment, sands are settled down completely, but the fines, that is mixed throughout the reservoir uniformly. So that's the mechanism we use. It's uniformly distributed, all the inputs within the reservoir. And then if there is some outlet from the reservoir, that portion of waste or suspended particles goes out along with the water flux towards the overland or towards the stream downstream. Once it passes to the stream downstream towards the overland outflank to the overland, the sediment again goes back. Yeah, I'm on the overland, or I'm in the stream now, and acts with the mechanism that I talked before accordingly. The settlement in reservoir, all these particles, we have the fall velocity, which is not the one we defined earlier, the trap efficiency, not that one. We have the fall velocity, and the equations are defined here, which is a balance between the weight of the object and the buoyancy force and drag force. And here are finally our simulation results from the well-studied experimental watershed, which is in Mississippi. We talked about this watershed yesterday, Goodwin Creek. We did a lot of initial verification in this watershed. Basically, the sediment portion we applied in GSSHA, a lot of those applicability of transport capacities and all those things comes from this watershed. Does this simulation run?
Sure.
Is this plugging
I think if you put the cursor over it, it should open.
or the time promise? Time is
Maybe not.
no worries. Just, yeah.
It shows sediment moving around the watershed.
Yeah. Yeah. We
don't have it?
No.
That would be a problem.
Yeah, that's
No,
that's our Sandy.
Yeah.
We
don't have that. It's okay.
We'll do that. No problem. Let's go ahead. Oh, no, that's okay. Thank you. Yep, where we are. Let's see this slide.
How-to section.
Sediment transport, right? So basically, it defines the process, how you define in the model, how you use the model in itself. So these are defining the Eurozone parameters. Again, it uses the index map that I talked and several presentations talked about. These are basically used for transport, the Eurozone parameter values, which for sediment, one of the main is the soil type itself. But there are a whole lot of parameters. A lot of those parameters from our rigorous experiment simulations, we keep it as default, which I talked before. This is the watershed, Goodwin Creek. This is how it looks, the overview. You know, it's fairly not settled, not developed, so, but a lot of farmlands and vegetation, especially trees around the stream banks. This is the performance of the hydrologic model with the sediment. Actually, this is hydrology. So now, why hydrology is important rather than sediment? You don't calibrate sediment itself first. The first place is you calibrate hydrology. You have the hydrology right, then you calibrate sediment, or you go to sediment. Otherwise, you are just getting the right answer for the wrong reason. Right? So stays or steps is first make the hydrology right. Go to the effect of hydrology. That's erosion. Here is the output from the hydrological model, the sediment. We got pretty good result in different magnitude of sediment or sedographs. This is a series of sedographs in long-term simulation, right? Sometimes a model can replicate or be good in one type of event. So if it it is calculating the big amount of sediment in a nice way, but it really underestimates or overestimates the small portion of actual observed data. But here you can see the tens of orders of magnitude pseudographs are captured well through the long-term simulation of sediment erosion. Some of the calibration validation results of observed and simulated volume of sediment, and some of the recommendations are here. The particle is not silica based, the gravity, specific gravity is not. So if it is not uniform specific gravity, England-Hansen equation, which takes account of all the fractions, I think, or that's what is meant here. That's the best if you want everything distributed and taken account. That is the physics-based equation. So you apply that. If you have observed sediment data to calibrate, likewise. We got really good result from Richardson equation, but there is always something for that good result. That is, we calibrated it, but the calibrated value then translate to the validation pretty well, right? So we recommend this is one of the really good equations, provided that it's empirical based and it needs calibration. If you have no observed sediment data, like I said before, for ungazed basins and all those things, and you don't have any parametric values to input, use the laboratory derived equations. So we have several of those in GSSHA as option. And the best one, yeah, and the best one we got is slope unit discharge equation. Probably we don't have to use in this internally though, the scaling factor, but for all the laboratory equations, we have used some scale factor.
That slope unit discharge works shockingly well,
Yeah.
considering it, you don't calibrate it. I was amazed, basically.
Yeah. Yep, that's right. And that was something like, it gave even better result than, you know, I mean, like, I think it's equally good with the well-calibrated Richardson equation for good.
Yeah.
We put that as a recommended portion. But the, you know, sediment being very important in so many aspects, we are further developing or enhancing the sediment process in GSSHA. Right? So these enhancements are, we're taking account of source and sinks, like I talked for the overland, also in the channel. So we are integrating the sediment that's also derived or developed in coastal and hydraulics laboratory. So we are including that. We already have coupled that. It has to come into release version. Also, we are looking into options. What happens? You know, it's an interesting topic. What happens when the concentration is too high? There is a term called Newtonian or non-Newtonian. In Newtonian fluids, the concentration, if the concentration is lower, what happens is the shear stress is a function of strain rate, right? And it's defined by a linear equation where the viscosity, which is the slope in that linear equation without the intercept, is a constant value because the slope is constant. But in non-linear, when the concentration really goes high, when that happens is in case of larva, right? The volcanic erosion, the larva type flow, or when there is fire, then after the fire, then it accumulates a whole lot of sediment because of the hydrophobicity, all those bigger fluids. And in that scenario, the Newtonian just breaks. And then the stress-strain relationship doesn't happen in terms of, you know, constant viscosity. The viscosity itself is dynamic in that case, or nonlinear in that case. So taking into account of that, we have to use the non-Newtonian kind of fluid flow. So we are also thinking or developing architecture in that prospect. So that's it for sediment.
Thank you.